We can calculate the types of metrics we've seen for each of these different representations and then compare them in terms of space efficiency. Now, the easiest metric to calculate, the most obvious one, is the total area A, but we've already seen examples of how misleading that metric can be. So we recommend instead calculating the size of the smallest labels within the representation. Okay, so the area of the labels on the leaf nodes. And if we do that and actually compare these different representations, we can rank them from best to worst. It turns out that the ranking depends on the quantity L, the aspect ratio of the labels involved. If L is close to 1 and we have squarish labels, then we end up with the ranking we see here, with tree maps on the bottom being the best, and the worst ones are at the top. So the worst representation in this set is the indented outline representation. If instead L is bigger and we have long, skinny labels, then the ranking changes a little bit. Tree maps still turn out to be the best representation, but now the worst one of the set here is the classical layered representation at the top. Now, space efficiency is not the only factor to consider when choosing a representation. There are other factors shown in the columns of this table here. For example, we may want all the labels to have the same orientation within the representation because that makes it easier to scan and read the labels. We may also want a representation that makes it very clear when two nodes are at the same depth or not. Okay, so if we want those, we may have to trade off space efficiency and make some compromise in choosing a representation from this set. There are also some practical design guidelines and consequences that are discussed in the article. We'll see a few examples here. One example is of this classical layered diagram. It turns out that by simply rotating the labels to be perpendicular to the levels of the tree, we can make the representation more legible. Okay, so on the left and the right here, the viewport or the window is the same total size, but on the right the labels look bigger simply because they've been rotated. Another example is shown here. On the left, you'll notice that the labels on the leaf nodes only take up a fraction of the area available on the leaf nodes. So we can shift the boundaries between levels without making any of the labels any smaller. We just shift the boundaries and then we end up with more area available to the shallow nodes, and in this case we're able to make the label on the root node bigger. Okay, so on the right we see the result of shifting those boundaries, and there's more area available to the shallow nodes without making any other labels smaller. Third example of how we can improve space efficiency and improve legibility is shown here. On the left we have what's called a squarified tree map. So in a squarified tree map, there's a special layout algorithm that is used to choose where the nodes are, and this algorithm tries to make the aspect ratio of the nodes as close to 1 as possible. Okay? Now this squarification process might not be a good thing to do if you want the labels to be big and legible and you have long skinny labels. Okay? If you have long skinny labels and you want them to be as legible as possible, you might want to instead do what we propose on the right, which we're calling a rectified tree map. So here we use a modified version of the squarified layout algorithm, and all it does is it changes the aspect ratio of the nodes to be closer to the aspect ratio of the labels contained within them, and that allows the labels to be bigger on average. Here's a final example. This is a very simple one. On the left we have labels that are made up of 2 words each, and the labels are long and skinny. If we simply introduce a line break within those 2 words, the labels are more squarish. They become more squarish, and that allows them to become bigger. So sometimes it may be possible to take the labels in a representation and modify them to either make them more squarish or more skinny so that they better match the aspect ratio of the nodes, and that can also improve space efficiency. Finally, there are some theoretical results of our work that are of interest. One of them involves tree maps. Now here we have a special type of tree map which we chose to analyze, and tree maps are often assumed to be optimal, and in fact they are optimal, for example, in terms of total area, because they do make use of all the area available for nodes. With respect to the labels, though, this particular tree map, which we analyzed, turns out to not be optimal, although it is the best that we could find. If we allow the depth of the tree to go to infinity, and we look at what happens to the total area of the labels, we find that it never exceeds 3/4. Okay, so that means there's always 25% of the area that's not used for labels. And so we wonder, is it possible to come up with a variant or a different type of tree map which would make total use of the area for labels, or at least do better than the 3/4 that we found in this case? So that's a question we leave for future work. Thank you for listening, and of course, you can find an electronic copy of our paper online if you'd like more details.